Good morning, ladies and gentlemen, and welcome to our initial product proposal for Seagull's drone, Mutish Ornis. We will first brief you on the team's structure, then a brief on the problem, followed by our thoughts and concepts and a first initial design. We will go through the functional and operational requirements of the drone, followed by a compliance cross-reference matrix and our camera choice and architecture. Our operational concept will follow threat and error management, leading to a preliminary cost and budgeting. Finally, our work breakdown structure and Gantt chart on the management side of the project will wrap up the presentation. There are 4 subteams in Mutish Ornis, namely structural, dealing with the frame and payload, avionics, programming and wiring the drone systems, simulation, creating a model of the flight in the event of circumstances beyond our control preventing test flights, and propulsion, responsible for researching, deciding on, and testing the motors and propellers for the drone.
The Seabird Ecology Group from the University of Liverpool, or Seagull for short, presented us with the mission to find a practical method which could be used to count cormorants to determine the change in cormorant nests on Puffin Island during the summer season. The 3 main objectives of this mission are to determine how many cormorant nests are found on Puffin Island, where these nests are located, and finally, how does the number of nests change during the summer. This will be vital as it will help seagulls' understanding on whether the environment on Puffin Island is changing, the impact of external forces on the ecosystem, as well as providing key information on the reasons why ecosystems are different. Seagull required the UAV to be portable as the mode of transport for travelling to the island is by small boat. Therefore, the drone should be collapsible as well as water resistant to prevent water damage from the sea spray. In addition to this, the UAV needs to be easily usable, so therefore requires simple flight mechanics and software to put less strain on the pilot's abilities in order to get the footage required. In 2018, when the BBC surveyed the island, they were only able to survey roughly 70% of the island. Therefore, a Seagull requirement is that the UAV needs to be capable of surveying the whole of the island, allowing no missing areas. As this project is likely to be run multiple times, the drone needs to be reusable so it can operate on missions with similar requirements. Finally, the ground sampling distance needs to be considered to ensure the video or image quality remains high. Therefore, a GSD of 0.82 cm per pixel or lower is required.
3 possible UAV configurations were considered: the multi-rotor, tilt-rotor, and fixed-wing. The multi-rotor offered great maneuverability, hover stability, but was susceptible to gusts and strong winds. Other UAV configurations posed issues with size, additional certification, and difficulty in acquiring photos at faster speeds. Moving parts in the case of the tilt rotor posed a higher chance of mechanical failure. Despite these drawbacks, the long endurance on offer and greater resilience to the winds was something to be commended. Based on the previous slide, the multi-rotor configuration pros and limited cons outweighed the pros of the tilt rotor and fixed wing. The drone shall contain 6 rotors. The 2 main reasons for this choice is because commercial drones need to have a minimum of 4 rotors, as well as to act as a safety precaution, as the UAV will still be able to maintain functionality and stability if a motor suddenly fails by shutting off the opposite motor, converting the UAV into a quadcopter, allowing the pilot to safely maneuver the aircraft. A gimbal capable of moving in dual axis shall be used on the aircraft. The functionality in a dual axis is more than adequate, as the aircraft will be able to yaw from left to right to change the field of view in the horizontal plane. The gimbal will then rotate in pitch and roll, decreasing complexity and the risk of failure. The UAV shall have an ingress protection rating of IP44. This rating is good at protecting the aircraft from foreign bodies larger than 1 mm while being protected by water splashes. The landing gear shall provide the clearance necessary to protect the camera and gimbal mechanism from meeting the ground, which could result in failure of components. Booms connecting the motor to the body must be detachable or foldable. This is to ensure we meet Seagull's requirements of the aircraft being compact and portable. The current design uses a pin system with a moving, screwable sleeve to hold it in place. However, this is subject to change after further research. For the landing gear system, an extended skid was chosen over a closed-end skid, as it would give a larger base for the center of gravity in case of side gusts during landing. The skids, which may include suspension to minimize impact force, also need to be high enough to it giving up clearance for the camera so it is protected when landing and taking off. Safety nets around the rotors were considered, however, as the drones will be flying in a secluded location with professionals, the benefits of the safeties do not outweigh the drawbacks of added weight and costs. The arms, main body plates and legs will be made of a tough, lightweight material such as carbon fiber or aluminium, and non-essential components such as the gimbal, electronic mounting parts and rain cover shall be made of PLA or ABS due to its ease of manufacturing and cheap material costs.
Requirements are divided into functional requirements, which is what the product is expected to do, and operational requirements. This is how the product delivers those functions. Both sets of requirements are derived from the customer's wishes and the regulatory laws.
The functional requirements due to the laws include that the product must not exceed the takeoff weight of 7 kilograms. The product should have a landing mechanism even in the events of an emergency. The parts that require changes, such as the propeller, batteries and motors, will need to be checked on a regular basis before being deployed for future missions. The functional requirements from the customer include that the product will produce legible footage roughly of 0.82 centimeters per pixel in quality. The footage format will either be in video, image or both. The cost shall not be greater than £650 for an on-land takeoff. The product will be compatible with open free software, therefore reducing the costs. The product will also be able to follow a pre-programmed flight path, which would include takeoff as well as landing. The operational requirements from the law. The Civil Aviation Authority allows the University of Liverpool to operate small unmanned aerial vehicles, subject to the Navigation Order 2016. Some of the requirements are that the product shall remain in the visual line of sight of the operator at all times, not exceeding 400 feet above the surface. Also, the customer must be briefed on the operation of the drone so they fully understand the risk involved in order to decide whether or not to participate in the operation. The operational requirements that satisfy the customer's needs include that the product shall be portable, meaning it can be stored and transported easily. The product should ensure minimum damage to the environment. The product should be easy to use and maintain. Also, the product shall be waterproof and shatter resistant and will have an SD card for easy access to the footage.
With the defined requirements, a methodology to track the compliance of the system is required. The verification cross-reference matrix lists the requirements and identifies the methodology verifying them. Listed is a snippet of the VCRM created for our system, and this will go further in detail as to the meaning of each heading. Our VCRM is arranged into requirement IDs. There are main requirements which are broken down into sub-requirements which contribute to the main requirements. The verification suffixes denote the quality control methods used. Inspection, review, analysis, modeling, simulation, demonstration, physical test, flight test, and software test are all the quality control methods we will be using throughout this project. Our success criteria details the basis by which our system will have met the requirement or not. This allows our success criteria to be verified by other parties through a similar method, rather than deriving an own way of checking if the requirement is being met. This tight integration between requirements and verification provides a vital link between the design process and quality assurance.
As per our initial cost estimate detailed later, we have come largely under budget due to deciding to make the frame ourselves. As a result, we have decided to utilise a GoPro Hero 9 Black action camera instead of the supplied Sony Alpha 5000, ascribable to a number of benefits. These include a 62% decrease in weight and 79% decrease in volume, permitting the option of using cheaper, less powerful motors and propellers subject to further design review, or additional avionics and waterproofing. The GoPro also provides slightly better GSD, of which proof is shown in the bottom right. The customer requires the drone to work in all weather scenarios. As the GoPro 9 was designed with excellent water and dust resistance in mind, there is no need to design casings or protection for the camera, allowing team members additional time to refine other parts and decreasing complexity. GoPro's hyper-smooth software lets the drone encounter gusts of wind and maintain a smooth, level horizon, and a long 91-minute capability in continuous recording grants the customer the choice of either activating the recording while the drone is on the ground, or remotely in the air via Wi-Fi without worry of the battery depleting midway through the mission. The drone's flight management computer, the Pixhawk 4, will be programmed with a predetermined path. Telemetry read from the RPM sensors and GPS will help it detect movement off path and will correct as necessary via speed controllers attached to the propeller motors. Data from an IMU, or accelerometer, will be used to send the gimbal controller instructions to continuously angle the GoPro as required to keep a steady and level horizon. The GoPro, if utilized in photo mode, is able to geotag captured images, which may help in stitching and analysis of the position of nests. Flight data will be sent via WLAN from the Pixhawk to a ground station computer, where the customer can monitor the progress of the mission and send a takeover signal to the drone if needed, enabling manual flight via an RC transmitter, recommended during the landing phase of the mission for a soft touchdown.
A risk analysis was performed to identify the factors that may have affected the success of this project. The probability of an event occurring was assigned a numerical value from 1 to 7, and the impact of an event occurring was also assigned a numerical value from 1 to 7, 1 being low and 7 being high. These values were then multiplied to give an overall risk level. The environment, avionics, and structure were assessed during the risk assessment. Some risks, despite the high risk level, are difficult to mitigate against due to the uncertainty of their nature. The course of action for each risk is stated in the risk modification plan and assigned to an owner, which is a team that will be responsible for reducing the risk and documenting the process and the results.
The drone will be taken to Puffin Island via a small boat packaged in a case lined with a custom foam cutout for the individual drone components. Once at the launch site, a simple written guide explains to the operator how to set up the drone for flight. The UAV is fully autonomous and begins the flight by taking off and climbing to 200 feet above sea level. It then initiates the first cruise segment to arrive at the east cliff of Puffin Island, ahead of a short descent to 100 feet above sea level for increased viewing resolution. If at any point the drone detects an error, it will immediately abort the flight and return to one of the predetermined landing points. Once the drone reaches 100 feet, it will initiate video recording of the east slope of Puffin Island. An estimated 34 minutes will be recorded at a resolution of 5K at 30 frames per second. Alternatively, still frames can be captured for use with geotagging and stitching into a panorama. Once the nesting area has been recorded, the drone climbs back up to 200 feet above sea level, where it begins the final cruise segment to the landing zone. The vehicle will land and autonomously shut down its motors, allowing the operator to retrieve the drone safely. Components for the main body are supplied from different sources. Building a custom frame is more cost-effective while ensuring a more reliable operation for the customer when compared to a pre-built frame.
The largest cost of the drone comes in the form of the GoPro Hero 9 camera. Its superior recording and stabilization capability outweigh the increasing costs. GNS was chosen for the GPS receiver instead of real-time kinematic data, as RTK requires an additional ground station which is prohibitively expensive. The initial cost estimate comes to just under £535, leaving a surplus of £115. This will be used for upgrades in motors and propellers.
Our work breakdown structure arranges the work in a systematic way whereby we can view all the deliverables and key milestones of the project and also visualize all the work which can be delegated to the different teams within our project group. The initial Gantt chart has been broken down to different phases in the project. Key milestones and tasks have been outlined. The green cells actually indicate tasks which have already been completed. The amber cells show tasks which have started and are in a work in progress. The red cells show tasks which are forecasted for future dates.
We appreciate your consideration for us to supply a vehicle to accomplish Seagull's mission, and hope this has provided some insight as to the design and capabilities of the drone. We welcome any questions you may have.